Hello, today I will be talking about style transfer, taking style of an image, like an artistic style of a Van Gogh painting, adding it to another image, like a head portrait of a person, and getting a new painting, as if it is a Van Gogh artwork. It is an old research field. However, with the advent of new deep learning methodologies starting from 2015, the field develops greatly, as I will try to explain in my presentation. Firstly, I will start with some definition and history about the field. I will briefly explain an old study to give an idea about the techniques used before the era of deep learning. Then a fundamental paper will be introduced. Um, this paper uses convolutional neural networks, CNNs, and it starts the research field of neural style transfer. It is a fundamental seminal paper starting the field. The way it works and loss metrics will be explained in detail. I will also exemplify that there are many successful industrial applications of the paper, and it has been improved significantly with the contributions of other researchers. Then I will focus on another approach in style transfer, generative adversarial networks, uh, GANs. This is a very popular idea in machine learning, and as Jan LeCun, director of Facebook AI, puts it, GANs are the most interesting idea in the last 10 years in machine learning. And this interesting idea has also an application in the field of style transfer. One of the many extensions of GANs, CycleGAN, uh, CycleGAN, with its consistency idea will be introduced in this presentation. Finally, I will talk about how the studies in this aesthetic-based research field are evaluated and compared with each other. Style transfer is categorized under a field called non-photorealistic rendering, NPR. Although it is argued a lot, people couldn't succeed in finding a new name to this upper class, and they define it in terms of its opposite, non-photorealistic rendering. So to understand non-photorealistic rendering, we need to first define what photorealism is. Photorealism in art is producing realistic images like the one at the background here. The image here seems like the output of a camera lens, but in fact it is a painting. So the opposite approach is to create images that seems like the output of an artist, like Monet or Picasso. Therefore, copying the style of an artist, including brush strokes, color choices, sketches, is called non-photorealistic rendering. For this purpose, people used various algorithms in the history before deep learning. Region-based rendering, example-based rendering, stroked-based rendering, image processing, filtering are some of the algorithms used in the past. I would like to briefly talk about some of these algorithms. Region-based rendering, it uses a variety of simple shapes like circles, triangles, squares, super ellipses, and so on. And these shapes are optimally fitted to each region of the photograph, as you see here. This provides an artistic style of some sort, but like many others, this is just one specialized artistic style. In general, these approaches these old approaches follow a certain algorithm that belongs to a certain style. Focusing on a certain style, unfortunately, they are not adaptable to various artistic styles. One exception might be example-based rendering here. Example-based rendering is looking for mapping between pairs. You need to have pairs. Both source and target image pairs. Although this technique is more generalizable when compared to others, it is limited by the training samples, in other words, examples. Moreover, it is not able to use high-level image features. One other algorithm is stroke-based rendering. It is the process of placing virtual strokes iteratively so that an image which looks like the original photo but with an artistic style is produced. I would like to illustrate it with an example study. The study of Hertzman, a current Adobe employee, exemplifies earlier studies of NPR, non-photorealistic rendering. In this study, first original image is blurred and presented as a target image to the algorithm. The algorithm tries to make the current image, which is probably a blank image at the beginning, get closer to the target by placing different bright sizes. There are many style parameters in this study, like the bright size and blur factor, and most importantly, it cannot simulate an arbitrary artistic style. To summarize, being unflexible was roughly the case at those times until the game changer joined to the game. Leon Gattis, currently working in Apple, et al. Published a fundamental paper in 2015 claiming that convolutional neural networks (CNNs) can be used to extract both artistic style from an artistic image and content information from a photograph. These two can later be combined to produce images that look like drawn by an artist, like Monet or Picasso. The groundbreaking part of this study is that it is not limited to certain artistic style, and this idea starts the field of NST, neural style transfer. Gattis et al. Used a pre-trained CNN network. The content and style images are provided to this network separately. They just use the convolutional part of the network. As the image moves in the network, it is being processed and certain layers hold different information about the image, like content information. Is there a face in the image? Is there a car in the image? While some other layers hold style information. As the style image is being processed in the same network, some layers hold style information, like what kind of colors are preferred, which kind of textures exist. That all together forms the artistic style of the image. By referring to certain layers of the network, they were able to extract content information from the content photograph and style information from the artistic image. Combined together, it gives an output like this cat. An image that looks like drawn by a certain artist, but in fact produced by computer. Let's move on how to extract content and style information. Gatis et al. Used VGG19 network, which has 5 stacks of convolutional uh, 5 stacks of convolutional layers followed by pooling. They have different depths like 64, 128 or 512. And as the image moves further into this network, spatial information becomes less important and content information appears. In fact, a CNN includes a neural network at the end, which converts this content information into the discrete classification output, but they do not use that part. Instead, they just take the content information from the photograph. When the photograph is presented to the CNN, they use this fourth stack, second layer, convolutional layer, to extract the content representation. What about the style representations? Here, the artistic image this time is provided to the same network. For extracting style information, they take all first layers of the 5 stacks. Each layer can hold a different aspect of the style, like color choices, brush strokes, or higher level information like the order of objects. Each layer is converted to something called gram matrix. For this purpose, first, spatial dimensions are flattened and then correlation matrix is calculated. This is a special mathematical operation. The resultant matrix holds the correlation information between the feature channels of the layer. There are 5 gram matrices and now they can be used in optimization, each of them with same or different weights depending on the level of style information that needs to be extracted. To be able to include them in the optimization process, loss matrix needs to be defined. Content loss is defined as in this formula. Yeah. This metric gets smaller when target and content image get similar to each other. Let me remind that it uses the fourth stack second layer output of the CNN. Style loss is also calculated similarly, but here we don't use just one layer of the network. We use 5 layers from different stacks. Here gram matrices are used. Since there are 5 layers considered, weighted sum calculations are as in this formula. Content loss and style loss are combined to produce a single metric for optimization. This metric guides the optimization process such that content from the original photograph is not lost in the target image, as well as the style information of the artistic image is not lost as well. Here you see an industrial application and its outputs. Ostegram is a Russian enterprise that utilizes Gatis paper to produce artistic images. They have free service, but in fact you need to get into a queue and it takes several hours to produce a simple image if you use the free service. It's very nice because these artists do not live now, but still we can have an idea about how it would be like if they paint us. There are other successful industrial applications of the same idea, like a phone app that became popular back in 2006, Prisma, or the Deep Art project, which includes the author Leon Gattis himself. Deep Art prints the artwork and sells it for considerable amounts of money. Here, the ethical question arises: who deserves the money? Van Gogh, Picasso, the algorithm developers like Gattis, or the developers of the VGG19 network? But this is a topic of another presentation. Let me move into other studies of style transfer. After the Gattis paper, many related papers have been published that improve the performance of the algorithm. For example, Risser et al. They find that gram matrix for an image is not unique. Different feature activations can give the same gram matrix, and this is the main cause of instabilities experienced during optimization. They introduce an histogram loss, which guides the optimization to match histogram wise as well. Similarly, Lee et al. Introduces an additional Laplacian loss for preserving the fine structures and details during stylization, whereas Kuhan et al. Introduces a Markov random fields that address the ability to use photographs instead of paintings as style. The improvements are not only about the optimization, of course. For example, Selim et al. Focuses on a specific application of the algorithm. Head point style transfer, head portrait style transfer. By imposing some special constraints, they try to get better results from the algorithm. To sum up, we have seen that how CNNs can give impressive results in terms of style transfer. Another popular approach is adapting generative adversarial networks to realize style transfer. The basic GAN structure includes a generator and a discriminator. Generator tries to generate images with a distribution close to the real images, whereas discriminator tries to differentiate real images from fake images. There are many versions of GANs, and not all are suitable for style transfer applications. For example, an approach called pix-to-pix is quite popular, but it requires pairs in the training set. Unfortunately, in our case, we don't have the original photos that inspire Monet, Van Gogh, and other artists. So we do not have pairs in our training set. Thus, we cannot train a pix-to-pix network for this purpose. Let's move to the other slides. There's another approach, however, called CycleGAN that requires no one-to-one matching in training set. It is very suitable for style transfer applications. Let me mention that CycleGAN in general is an image-to-image translation method, and it has many applications. Style transfer is just one application of CycleGANs. In general, they can be used for many more transformations like day to night, summer to winter, apple to orange, or horse to zebra. However, for the purpose of this presentation, I will just focus on style transfer application. In CycleGAN, there are two adversarial networks as shown in the figure here, which belongs to you see one network here, and a repetition of it with different input here. Here the first network takes the image in X domain and translates it to Y domain. The X domain can be the domain of Van Gogh paintings, for example, and Y domain can be real-world representation of that image. The second network translates the image in Y domain back to the original X domain. If both networks work correctly, the end result of this network should be similar to the original input. Cycle consistency idea is based on this assumption. For example, if you translate a Turkish sentence into English and then back to Turkish, the result should be similar, if not the same, to the original sentence. The name of CycleGAN is derived from this concept. CycleGAN idea is repeated, as shown here on the right. This time, starting from Y domain, and this after converting it to X domain, G takes it back to Y domain. Again, cycle consistency loss is calculated, and this loss, as well as this loss, is used to guide the networks. As seen in this slide prepared by the authors, horse in X domain can be converted to a zebra in Y domain, then back to a horse in X domain. We have a set of horse pictures and a set of zebra pictures. But the most important part is they are not paired. Cycle consistency ensures that horse to zebra and zebra to horse translation give similar results. For example, in this case we have small cycle loss. However, in this case we have large cycle loss. And these cycle loss calculations will guide the network optimization. Here we see how four famous artists would draw the photograph on the left. The results are impressive. One of the most important features of CycleGAN is that it doesn't require one-to-one mapping. This makes CycleGAN a good alternative to neural style transfer. However, there is one fundamental difference between the two approaches. I mean, neural style transfer, which uses CNNs, and CycleGAN, which uses generative adversarial networks. There is one fundamental difference between them. NSD is a one-to-one style transfer technique, whereas CycleGAN requires training on collection of images. In other words, NSD is looking to one Van Gogh image and then producing the output. Whereas CycleGAN is looking to entire Van Gogh artworks to extract his style. As you see here, both give impressive results, but with different approaches. As mentioned earlier, style transfer is just one application of CycleGANs. CycleGANs can be used for many other purposes. An interesting one shown here is from paintings to photos. Since it is a cycle concept, instead of going from photos to paintings, you can also go from paintings to photos. To summarize, CycleGAN is a very successful extension of GAN, Generative Adversarial Network, and it has many applications including style transfer. This brings me to the final part of my presentation. The final part is about how we can evaluate a style transfer study. There is no easy answer for evaluation. Quantitative evaluations are biased. Qualitative evaluations are biased. since they depend on the aesthetic judgments of researcher, or if it is a user study, participants like gender, age, education, and many more parameters are influential on the evaluation. Quantitative evaluation metrics, they compare runtime or convergence speed. In addition, they may look at loss function. However, the values of loss function outputs may not always be a good indicator of output image quality. Some studies may work with limited styles, and thus being able to work with arbitrary styles, style scalability is another measure. Although the definition of arbitrary is qualitative. To sum up, there is no precise metric that everybody agrees on, but this is quite natural since this field is more about art than mathematics or engineering. This is the end of my presentation. Thank you for listening. The main literature survey reference I benefit a lot is this paper, but there are many other papers and I try to refer them in the slides. Finally, if you are someone who like watching instead of reading, here are some YouTube videos about the fundamental paper of neural style transfer. Thank you again once more for your attention.